In this video, we're going to discuss CRA models for whole number division algorithms. There's going to be three different ones that we'll look at. This first one will be the partial quotients. Sometimes you'll hear it referred to as the Big 7 strategy because our abstract model contains what looks like a Big 7. But for this one, it's essentially going to be kind of a combination and just more of a written record for the decompose, the dividend, and the repeated subtraction strategies kind of paired together. So, so for this, we have 42 divided by 6. So we have 4 10s and 2 1s. Essentially, kind of what we're trying to think of is kind of easy multiples of 6. If we wanted to, we could just subtract 6 at a time. Take away 6 from the model, trade all of our 10s out for 1s, take away 6 at a time, and kind of keep track of that in here. I'm going to do it in just 2 steps just to save on time a little bit. But we'll say from these 42, maybe I know that I can create 5 groups that have a size of 6, and that would require me to take away 30 of these base 10 blocks over here. Okay, so in the concrete model, kind of what we would do, we're not able to, if we're going to look at size or groups with a size of 6 or 6 groups, either way we can't leave these 10s as 10s. We need to think of those as, instead of thinking of those as 4 10s, think of those as 41s. So I'm actually going to swap all of these out. And again, it's because since we just have 4 10s, we can't put 1 into each of the 6 groups and keep them equal if we're going to think of that divisor as the number of groups. If we're going to think of that divisor as the size of each group, we also can't leave the 10s as 10s because we need to be able to break them apart into 6s. So, okay, so we still have 42, but we'll say we're going to kind of think of these in 2 different chunks. Maybe I know if I take these 30, I can create 5 groups that have a size of 6. Okay, I'm going to try to kind of set them. So there's 6. I'll kind of set these aside. Okay, so there I've taken away 30 from my original quantity of 42, and I've created 5 groups that have a size of 6. Okay, so from the 42, right, this is kind of what we do in the algorithm then. We're going to take 42 minus 30, so 2 minus 0, going to be 2, 4 minus 3 is going to be 1. Okay, so, and that aligns, that 12 aligns with what we have remaining in our group. Okay, and then in this partial quotients or Big 7 strategy, over on this right-hand side, so kind of why we have this vertical line here is because we're kind of right in line with this 30. We want to designate that this 30 created 5 groups of 6. Okay, so over here, if I'm going to say that 6 is the size of each group, over here I'm tracking how many groups with that size I made. Okay, so now I just have 12 left, so from the 12 I can make 2 groups that have a size of 6. I might have to scoot these over just a touch so I have room to finish my algorithm here. So I've taken the remaining 12 away, right? And I have 0 that's left in that original model. And then those 12 that I just placed down, I created 2 groups that have a size of 6. Okay. So then if we add all of these together, right, so it doesn't matter what we pick for steps. We could have just done, a group of 6, a group of 6, a group of 6. We'd have a bunch of 1s over here. We'd have 7 1s. Right, so then we can write our quotient up on the top there. Okay. So I see this was the concrete version. This was the concrete model. This was the abstract model. Just in the sake of time, I'm not going to show the representational models for any of these algorithms, but it would, kind of follow that same sort of structure we'd start with 42, and then we transition this into all of our 10s. Right, so that's one of our 10s turned into 10 ones, and so on. And then we can cross them out as we kind of organize them into groups that have a size of 6. Right, so those are partial quotient algorithm. Next one we're going to look at is the standard algorithm. Okay. So again, I'm going to show the concrete and the abstract side by side just to help make sense of that abstract model, and then we're not going to show the representational model for this one, but it'll just be drawings of the base 10 blocks that would align with the moves that we're going to do. So for 156 divided by 6, right, most of us probably know that we start with our largest place value, and we're trying to think of, right, common language you might hear is how many times does 6 go into 1? Or as we move on, how many times does 6 go into 15? Right. So kind of what we want our students to be able to think, the perspective to approach this is, if I have 100, and generally it's going to be easiest to think of this standard algorithm as the fair sharing division, so 6 groups. Okay, so the number of groups is our divisor. So one way we can have students think about this is, if I have 100, how can I place that into 6 groups equally? Okay, so I have 100. I can't create 6 groups and keep them equal if I leave this as 100. Okay, so I need to trade that for 10 tens. Okay, so I need to ungroup this. Okay, so instead of having that 100, I'm going to have these 10 tens. Again, the reason I can do that is because I haven't changed the total number of little cubes that are in my model. I still have 100 here, and then 50, and then 6 over here. Okay, so again, in the algorithm, kind of you might think of, some might think of how many times does 6 go into 1? Well, 0 doesn't go into any. We could write the 0 up here, and then now we just think of this as 15 tens. So we want to kind of relate that back to actually what's happening in the model. So now I'm thinking of this as 15 tens. So I was just looking at this one place value. Now I'm looking at these 2 place values here. Okay, so if I have 15 tens, how can I divide that into 6 groups equally? Okay, move this up just so I have a little more room down here. Okay, I'll try to, groups are going to be a little cramped on here, but so those are 3 of the groups. We'll kind of go up on the bottom of the board there, and then these are going to be 3 others. Okay, so I've placed 1 10 into each of the 3 groups. Since I have 15, and maybe I saw, well, I can take 12 right away and put 2 into each of those groups. Okay, and then I have 3 10s that are still left in my original quantity here. But these, I can't put the 10s in any of these equal groups and keep the groups equal. Right. So kind of what this looks like in the algorithm then. Right, I've put 2 10s into each group, and the total number of 10s that I have taken away from that original quantity is 12, right? 6 groups of 2. So I've taken away 12. So we're going to subtract 12 from that 15. And I have 3 10s remaining, right? That's where this do 2 times 6 and then subtract that from this total here. That's where that comes from in the algorithm, is we're trying to figure out how many 10s do we still have remaining so that we can move on to the next step. Okay. So again, these 10s then will need to be regrouped because we're not able to keep them as 10s and place them into those equal groups. Okay. So we're going to exchange these for 10 ones, if I can grab them. I'll just have them. Alright, so that's one that I've exchanged. 110 for 10 ones. There's another 10 ones. And the last set of 10 ones here. Okay, so that move in this concrete model here, this exchanging our 310s as 31s, right? Because then some of you might know, well, the next step in the algorithm, we just say, well, bring down this 6. Right, so that move there is our way of saying we're no longer thinking of this as 310s, but we're thinking of that as 3010s or 31s, and now we need to also include the other ones that we had in the model, because now we're going to try to subdivide these ones into these groups. Okay, so now I have 36 ones. I want to think, how many ones can I put into each of these 6 groups? Okay, so if we didn't know, we could go one at a time, putting them into each. Just to save on time, we're going to say that we know 36 divided by 6 is equal to 6. I'm actually going to rotate these around a little bit as we go. So I'll take 6 ones and put them into each group. Move these over. Okay, so from those 36 ones, right, what we did was we placed 6 ones in each group, right? This is where we're recording our group size, 6 ones in each group. And then again, we're told you do 6 times 6, and then whatever that product is, you subtract that from here. Again, why we're doing that is because we're trying to figure out how many ones from that original quantity have we divided into those groups. Okay, so we put 36 ones into those 6 groups, and then some 36 minus 36 is 0, right? That 0 is saying we have nothing from that original amount that still needs to be placed into those 6 groups. Okay, so again, this idea of kind of moving to the next place value, that's what we're doing, that ungrouping, or bringing down a digit. That's where we're doing ungrouping, right? We were first thinking of this one as 100, and then we were thinking of it as 10 tens with this 15 tens. Same with this 3. This used to be 3 tens. When we brought this 6 down in this algorithm, that was where we are shifting our mindset from thinking of 3 tens to 31s, and then we have those other 6 ones we need to consider. Okay. And there's just one more I wanted to show. It's the explicit trade algorithm. And I'm going to actually, I'll kind of bring this one back into, so we can kind of go back on that, just so I don't have to redo all the models again. So, but with the explicit trade algorithm, it's going to follow the exact same steps as our standard algorithm. But we're just going to be more explicit with when that trade or that ungrouping is happening. Okay, so still set up in the exact same format. You might notice I space these out a little bit more. Sometimes with this model, you might see this organized in columns as well. So this model is going to, or this algorithm is going to be a little bit easier for students to understand, kind of place value, and trying to think of this as hundreds and tens and ones. Okay, so again, if I had 100, right, the first thing I did in that concrete model was I ungrouped this and thought of that as 10 tens. Okay, so in the explicit trade algorithm, right, we're actually gonna just cross these off. So rather than thinking of this as 100 and 5 tens, I'm just going to think of that as 15 tens, right? Because that was that first thing, and it's not really on this model anymore. Right, that first thing I did, I had this 100. I exchanged that for 10 tens. Right, I ungrouped this. So then I had a total of 15 tens in my model. Okay, so this explicit trade algorithm follows the exact same steps as the standard algorithm, but again, the reason it's called explicit trade, it makes the trade more explicit by crossing it out and rewriting the 15 in that tens column, just highlight that as tens. Okay, so then what I did was I put 2 tens into each group. All right, that means that I took 12 tens away, and then I had 3 tens remaining. Okay. And then for this next step again, I had 3 tens remaining, and then I had to, right, I have all these ones in this model. That next thing that I did was I took those 3 tens and I ungrouped those or regrouped those into 30 ones. And then I had an additional 6 ones, right? So if you want, we can still kind of bring this down, or you can cross off from that step. But from here, you can cross off here, and we'll rewrite 36 in the ones column again, just to better highlight that we now have ones. Okay, then we put 6 ones into each of the 6 groups. That took away a total of 36, which left me with 0 ones. Okay, so the concrete model for the explicit trade is going to be the exact same steps that I went through in the standard algorithm. The only difference is that we are just highlighting what we're doing a little bit more according to place value there. So again, those are the concrete models and the abstract models. Again, the the representational models would just be drawings of those base 10 blocks and crossing out, showing that regrouping. I didn't show them just to save on time, and they are a little more tedious for larger numbers like this, where you have like a 3-digit dividend. But those are kind of some of the common models for those division algorithms.